To re-emphasize, for the extratropics then, with the scaling we used for Rossby number being much smaller than 1, the thermodynamic perturbations are fairly small. Essentially, if you're in a geostrophic balance or quasi-geostrophic balance, then that has to be pretty much true, because you are balancing pressure gradients with Coriolis. You cannot have large thermodynamic perturbations. Using then the thermodynamic equation, we can derive the scaling for vertical motion that we already saw. So the vertical motion is related to the horizontal motion through this relation where R0 is much less than 1. Okay, so this Richardson number is the term that is relating the potential energy to the kinetic energy. Typically tends to be the vertical shear or the horizontal gradient of temperatures, okay, which relates to vertical shear through thermal winds. Let's now move into the tropics, where the Coriolis effect drops significantly, reaching 0 on the equator. This becomes a big issue, because then Rossby number has F in the denominator, so Rossby number is going to get larger. That has to be kept in mind. Looking at our horizontal equations of motion, then the pressure gradient term, the Coriolis, and the geometric terms, and the dissipation terms for the zonal and meridional directions. Scale it with the horizontal velocities and horizontal scales of motion, which is related to the pressure gradients, so that the pressure gradient term is related to the acceleration term and the background pressure, which is the Froude number. So we have again the Rossby waves, gravitational wave speed relative to the motion of the fluid itself, and the Rossby number is order 1. So for these larger Rossby numbers near order 1, we will see that even in mid-latitudes you get these tight low pressure and high pressure mesoscale systems where Rossby number gets pretty close to 1, and then the flow is not geostrophic anymore. Maybe I'll show a figure in the next podcast, but you can find many of those if you go on Google and look for daily flow fields on, let's say, 500 hectopascal surface. You will see lots of these small scale features which are related to that Rossby wave we saw in the jet stream and so on. Continuing this, delta P over P0 then again can be written as delta rho over rho 0 using our hydrostatic equation, which is related to delta theta over theta 0, the thermodynamic perturbation, which is 10 to the minus 3 for R0 equals 1, which is even smaller than what we saw in the extratropics. Going to our thermodynamic equation with that, the one we wrote already several times, we can scale the quantities again. U squared over L times the Froude number is again vertical scale of motion versus the static stability, so that vertical scale is related to U over L times 1 over Ri, because R0 is equal to 1 here, which looks similar to the extratropical vertical scale we had derived from the thermodynamic equation. But here U over L delta theta or theta 0 is approximately equal to the vertical motion times the Brunt-Väisälä frequency or the static stability. Right? Why are we doing that? It's much more important in the tropics because the static stability is going to determine the vertical motions. Essentially, when you have instabilities, you can drive baroclinic structure and motion, but for that you need convection, and then convection has to be explained in terms of stability, so it's kind of a convoluted argument. Looking at the continuity equation scaling then, We can write delta rho over rho 0 as delta P over G times the vertical scale divided by rho 0. We are again using the hydrostatic balance here to go from delta rho to delta P over G. You should be very familiar with that by now, which is the Coriolis times horizontal scales divided by the vertical scales, again relating delta P, which is Froude number divided by the Rossby number. And thermodynamically, again, that relates to the perturbations to the potential temperature divided by theta. Okay, remember those zonal mean meridional sections and the tropical structure, which was nearly barotropic. So we are still struggling to generate vertical motions or the coupling in the vertical in the tropics given the barotropic structure. So that's again Froude number divided by R0. Rewriting that here, this was for the extratropics. Thermodynamic perturbations were small for geostrophic regime, whereas in the tropics the thermodynamic perturbations are related to the Froude number or the gravity wave speed relative to the speed of the horizontal motions of the tropical atmosphere. In that case, the approximations can be used in the continuity equation to write. Remember, we had d rho dt plus 1 over rho divergence of the horizontal flow field. Then the d rho dt term becomes 1 over rho 0 d rho 0 dw dz. So the perturbations to the density field is coming from these vertical motions, where again, of course, the horizontal divergence is d dx plus d dy, where we are looking at the geometric terms gone, and the horizontal flow field is of course ui plus vj, where I and j are the local unit vectors. You have to get a sense for how these things work. We will do that as we go forward. These mathematical derivations can be a little bit dry, but we have to run through them so that when we actually get to the rich physics, we have these things in mind. What are the scales of tropical dynamics in the atmosphere and the ocean? Ocean does turn out to be much simpler. Atmosphere moves fast and it has this huge nonlinearity of moisture dynamics, which is not there in the ocean. So this is why we have to understand the scales and the balances in the tropical atmosphere and the kind of paradoxes or conundrums that remain in terms of generating motion in this barotropic, near barotropic system.